One of the properties that's very prominent when you're dealing with gases is the property of pressure. So gases exert a force on their containers, and pressure is something that measures force per unit area. A Pascal is the unit of pressure that relates to SI units. So our SI units that we're working with are mass being kilograms, length in meters, time in seconds, temperature in kelvins, and amount of a substance would be moles. Two other properties that we're not dealing with that you might see in physics class: electric current is in amperes, and luminosity is measured in candela. Any other property that you have is a combination of these 7 properties in some sort. Like, for example, volume is length cubed, and so we can just relate it to length. The official SI unit for volume would be meters cubed. So a Newton is the unit of force that relates to SI units, because 1 Newton is 1 kilogram of mass being subjected to 1 meter per second squared of acceleration. So newtons are related to kilograms, meters, and seconds, and now we're down to the most basic SI units. And then 1 Newton per square meter is a Pascal, which, if we relate it back down to these most basic SI units, would be a kilogram meter per second squared. This is a Newton, kilogram meters per second squared, over meter squared. And so we can cancel out a meter here, and then we get kilograms per meter second squared. So this would be a Pascal. And it's kind of cool that it relates to the basic SI units, but it's a very small pressure. And so you'll notice that an atmosphere of pressure is not only a kilopascal, which is 1,000 pascals, but it's 101 kilopascals. So pascals are very tiny measurements of pressure. Most gases that you work with are just a whole bunch of pascals. So historically, we've had other units to measure gas pressure. It kind of makes sense to deal with gases and how they relate to the pressure of the air around us, being 1 atmosphere. Also, millimeters of mercury. A lot of times gases historically were measured using columns of liquid mercury, which were, quite heavy and dense. And so measuring gas pressure with a column of mercury, either in millimeters or in inches, historically was very useful. If you go to check your tires, you might get the pressure in pounds per square inch. So like British units historically have been used in this country for pressure. We also have torr and bar, a lot of different units for pressure. So let's make sure that we know how to convert units. We're going to try to figure out how many millimeters of mercury this is. So let's do it with a few digits, because our relationships up here have at least 6 digits. Let's try taking 6 digits here. We don't have pascals in any of these relationships up here, but we do have kilopascals, and kilo is 1,000, 10 to the third. So 1 kilopascal is 1,000 pascals. And 101.325 kilopascals is 760 millimeters of mercury. What this means is that 1 Pascal of pressure would be enough to lift a column of mercury against the force of gravity by 0.0075 millimeters. So that is not a lot of pressure. Even though mercury is heavy, lifting it by just 0.0075 millimeters is not very much. So that is why we usually deal with kilopascals if we work with SI units in our pressures. All right, here we have another conversion. I usually work with millimeters a lot more often, so my habit is to convert this to millimeters and then to atmospheres, but we do have a relationship above directly with inches to atmospheres. I think the answer key to the note packet does the 2-step conversion, but we can get the same answer with 1 step. It comes out to be 1.004 atmospheres. historically, we have measured pressures. One of the ways we've measured pressures is with columns of liquid, because a column of liquid would exert a certain pressure. The mass of that liquid over the area that that liquid is on top of, depending on how thick or wide the column is. That pressure is a measurement of the air pressure around it, because if we have a container of fluid, I have tried to draw a container of fluid here, some sort of liquid, and if you've ever done this with a straw, kind of, dipped a straw into fluid and then capped it off and then tried to see if you could lift it. If we have no air in here and we have air outside pressing on the liquid, then you can draw up some liquid into this column. And how high this liquid can be drawn depends on how much pressure the air is around the rest of the container, the rest of the liquid in the container. And so this is how the pressures of air were measured. If you use a kind of a less dense liquid like water or alcohol, you can get quite a large column, and then that's a little bit difficult to work with. So historically, that's why mercury was used, because it is so dense and heavy that you can measure fairly significant pressures with columns of fairly manageable heights. So the pressure that a column of liquid is exerting is proportional to the height. A column of liquid that is 20 centimeters high is exerting twice as much pressure as a column that's 10 centimeters high. Also, the density of the liquid has something to do with it. If you have a liquid that's twice as dense, it's going to give twice as much pressure. And then the acceleration of gravity, if you were trying to measure the pressure somewhere else where the gravity was not as much of an effect, if you went to the moon to measure pressure, that would affect the pressure as well. So we're going to figure out how high a column of mercury we can pick up with an atmosphere of pressure, or we'll figure out what the pressure is of a certain column of mercury. So the density of the fluid needs to be in these SI units, because we're going to be getting the pressure in pascals, which has SI units. We mentioned that before. And mass is kilograms, not grams, and volume in SI units would be meters cubed, so not milliliters. We know that 1 milliliter is 1 centimeter cubed, and we also know that 1 meter is 100 centimeters, so we're going to have to cube this relationship to get centimeters cubed and meters cubed, because 1 meter cubed is not 100 centimeters cubed. And we also know that 1 kilogram is 1,000 grams. So let's go ahead and do this conversion. We can convert milliliters to centimeters cubed fairly easily. The 100 centimeters to 1 meter I mentioned has to be cubed so that we can get cubic meters. And then we have to convert grams to kilograms. So when we cube this, our unit's going to end up with cubic centimeters and cubic meters. So the cubic centimeters are going to cancel and milliliters cancel. So this will give us kilograms per cubic meter. And we end up with 13,600 kilograms per cubic meter. All right, now that we know that the density of mercury is 13,600 kilograms per cubic meter, we can use it to figure out the pressure exerted by a column of mercury. So our formula that we had before, the pressure is equal to the height times the density times the acceleration due to gravity. And gravity has an acceleration of 9.81 meters per second squared. And the height that we want to calculate for is for 760 millimeters, this famous number that we are using a lot in our conversions. So we want to see how much pressure is that. If we had an actual 760 millimeter column of mercury, what kind of pressure would that be exerting? And so to get this pressure into pascals, it's helpful to convert everything down to these basic SI units. So instead of having the height in millimeters, we're going to go ahead and make it meters. So this would be a 0.760 meter column of mercury. And so now we have everything in kilograms and meters and seconds, and this is going to make it a little bit easier to convert to our pressure units. So the pressure is the height, which is 0.760 meters, times the density, which is 13,600 kilograms per meter cubed, times gravity, which is 9.81 meters per second squared. So we have 2 meters in the numerator. I'll go ahead and cancel those with 2 out of the 3 here in the denominator. And this comes out to be 101,396 kilograms per meter second squared. We only have 3 significant digits here, so I'll underline that. And then we're told up above that a Pascal is a Newton per meter squared, which is a kilogram per meter second squared. So instead of putting a slash in the denominator, I'm putting that in the numerator. So 1 kilogram per meter second squared. So this is 101,396 pascals. These units here, a kilogram meter second squared, is the same thing as a Pascal. So we just switched the units there. And then let's go ahead and convert this to kilopascals and then atmospheres. There are 1,000 Pascal in a kilopascal. And there are 101.325 kilopascals in an atmosphere. And this turns out to be, with 3 significant digits, 1.00 atmospheres. So an atmosphere is enough to raise a column of mercury that is 760 millimeters high. So that is why we say that the conversion between 1 atmosphere and millimeters of mercury is 760 millimeters of mercury to 1 atmosphere. All right, so why do we use mercury? Historically, mercury was used instead of something more safe and less toxic like water, and that's because 760 millimeters of mercury is 76 centimeters, a little bit less than a meter, so a little bit less than 3 feet, so that's something that you can work with. Let's see how high the column of water would be. So we're going to relate the height of the column to the pressure, that 1.01 atmospheric pressure, with this relationship. Let's go ahead and solve for the height. So we're going to need the pressure, and we're going to need the density and the acceleration due to gravity. Let's see if we can get these in units that are going to cancel. All right, so the pressure is given in atmospheres, 1.010 atmospheres. We can convert this to kilopascals, and then we can convert that to pascals. So that ends up being 102,338 pascals with 4 significant digits. I'll just underline that. And remember that a Pascal is 1 kilogram per meter second squared. So the pressure is actually equal to 102,338 kilograms per meter second squared with 4 significant digits. Now we need rho, the density of the liquid. We're being told it's 0.9980 grams per milliliter. Again, we need kilograms and we need cubic meters. So let's go ahead and convert that. So there's 1,000 grams in a kilogram. A milliliter is the same as a cubic centimeter. There are 100 centimeters in a meter, and we need to have that cubed. And that comes out to be 998.0 kilograms per meter cubed. The force of gravity, we are already told in the proper units, it's 9.81 meters per second squared. All right, so let's put in the values with the proper units into this equation. Here we have the pressure, 102,338 kilograms per meter second squared. The density is 998.0 kilograms per meter cubed. And then gravity is 9.81 meters per second squared. So we have 2 meters in the denominator, 3 in the numerator. We'll go ahead and make this a 1 and cancel these other ones. Our seconds squared are going to cancel. Our kilograms also cancel. And so we are left with just meters, which is something that height can be in. And this ends up being 10.5 meters. So that is like 30 feet. That's as big as a 2-story house. So it's kind of inconvenient to work with scientific instruments that are as tall as a 2-story house, which is why having something that was, less than 3 feet was a lot more convenient for scientists to work with. One of the instruments that scientists used to work with was a manometer. So we would have a sample of gas and a U-shaped tube filled with mercury, and they could come in a closed-end manometer or it can be an open-end manometer. The thing is that if it's an open-end manometer, you need to know what the atmospheric pressure is in the room that you're working. So you also need a barometer somewhere to be able to read that. If you have a closed end, then the pressure is 0. This is supposed to be a vacuum. There's no air inside here. So those are the 2 types of manometers that you could have. We don't have any at MJC, but I used to work with one quite frequently when I was going to school. It seems like it's very confusing to students, though, how to actually read what pressure your sample of gas is with the manometer. And you can just kind of think of it as these two gas samples are having kind of like a tug of war, only it's a pushing tug of war. So we have one gas pushing on one end, another gas or lack of gas pushing on the other end. And so whichever one is pushing down further is a stronger pressure. Okay, so we only have one possibility for a closed-end manometer. There's no way that a vacuum with no gas in it at all could be pushing stronger. So whenever you have a closed-end manometer with a vacuum on the closed end, then the gas end of the manometer is always going to be lower. It's always going to be pushing harder than no gas at all. If you have an open-end manometer, you have 2 possibilities. You could have your gas sample not pushing quite as hard as the atmospheric gas, or you could have the gas sample pushing harder than the atmospheric gas. So there's 2 possibilities here to figure out what the gas pressure is. All right, so manometer A is the closed end. So we have the gas pressure, and that is larger than the vacuum pressure. And it's larger by a height of 213.5 millimeters of mercury. So the gas pressure is equal to the vacuum pressure plus an additional 213.5 millimeters. The vacuum pressure, since there's supposed to be no gas in there at all, this should be 0. So the gas pressure should be 213.5 millimeters of mercury, because it's beating the number 0 by 213.5 millimeters, and so that number is 213.5 millimeters of mercury. Now we just have to convert this to atmospheres. There are 760 millimeters of mercury in an atmosphere, and that ends up being 0.2809 atmospheres of pressure. All right, let's take a look at these diagrams before I have to scroll down. So here the atmospheric pressure is beating the gas pressure. So the atmospheric pressure is larger than the gas pressure by this value of H. So for manometer B, the gas pressure is the atmospheric pressure minus this height. It's less than the atmospheric pressure by this height over here. For manometer C, the gas is beating the atmosphere by that height. And so it is larger than the atmospheric pressure, so we are going to add that height to the atmospheric pressure to get what the gas pressure is. So this one, the gas pressure is smaller by that amount h. We're going to subtract that amount h. And in this scenario, the gas is larger than the atmospheric pressure by the amount h. Okay, so we can't really see the drawings, but I have the notes left behind, so hopefully we can make this work. All right, so for B, the gas pressure is going to be the atmospheric pressure minus the height. So we have 759.3 millimeters of mercury minus the height, which is 336.8 millimeters of mercury. So that is 422.5 millimeters of mercury. So that is the pressure of the gas. We wanted to have that pressure in atmospheres, so we can just use the 760 millimeters to 1 atmosphere conversion factor, and it is 0.5559 atmospheres. So on that same day, with that 759.3 millimeters of mercury atmospheric pressure, we have another gas sample, and that one is higher than the atmospheric pressure by 184.1 millimeters of mercury. So that makes it 943.4 millimeters of mercury. And then when we convert that to atmospheres, we get 1.241 atmospheres of pressure.